Hello everyone, and welcome to the new episode of our series of solving LeetCode Daily challenges. And today we're going to solve a problem called all nodes distance k in binary tree, which has medium difficulty. Okay, let's move to the problem statement. We are given a binary tree defined by its root, and we are given some other node called target, and we are also given an integer k. And we need to return the list of values of all of the nodes that are located at a distance of exactly k from our target node. Let's look at the constraints. So the number of the nodes in the tree is relatively small, up to 500. The values are also small and they are all unique, which is important, and our k is up to 1000. Okay, so that's a pretty standard tree problem, and I hope this video will bring some good educational content for you guys. So let's take a look at how to solve this problem. So at the beginning, let's consider a very special case, when our target node is the same as our root node. And in this case, to solve this problem, we can define a recursive function that we will call find nodes at distance, and it will take exactly two parameters: our current node and our distance. So if our current distance is equal to 0, this means that we have already found one of the nodes that belong to the answer, and we will just add this node to the result. And if the distance is bigger than 0, then we will call our function recursively from both of our child, from our left child and from our right child. But we will make our problem smaller by decreasing its distance by 1. So yeah, for example, if we need to find all of the nodes that are located at a distance 2 from our root node, then the problem is equivalent to finding all of the nodes that are located at a distance 1 from both of its child nodes. And the answer is obviously 6208. Okay, so now we know how to solve our problem for this specific case. But what about the general case? What if our target node can be any node? For example, suppose that target node is equal to 5, just like in one of the sample examples. Okay, what changed? Only one thing changed. Now, in our recursive transitions, we should go not only to the child, but also to our parent node. Because, for example, suppose that k is equal to 1, then the result is not only 6 and 2, but also 3. And suppose k is equal to, the result is not only 7 and 4, but also 1. So that's the only thing that changed in our function, and we will actually reflect it in our code. So we need to add one more recursive call for the parent of our node, and also we need to decrease a distance by 1. And basically that's it. That's all that we need to do in here. Of course, there are some implementation details that I will cover shortly, but the general idea is this. We have a recursive function, and we either have already found our result, or we make 3 recursive calls to our left child, to our right child, and to our parent. Okay, let's take a look at the implementation. So the first thing that we will need to do is to notice that our tree node has a link to its left child, right child, but it doesn't have a link to the parent. So we will need to populate these links ourselves. And to do that, we will heavily use the fact that all of the values are unique, and we will implement a recursive function called collectParentData, which takes exactly 2 parameters, our current node and its parent. And the base of the recursion is simple. If we are in the null node, then we can just return from the function. Otherwise, we have this map called parent node by value. The key to this map is the value of a specific node, and the value of this map is actually the link to the parent node of our current node. So we just put this information in the map, and then we call our function recursively from our left child and from our right child. And for both of our children, the parent node is actually our current node. Okay, so now we have this map that contains the parent information for each of the nodes. Then we are good to go to implement our find nodes at a distance function. So let's do that. As explained, it takes exactly two parameters, our current node and distance. So our base cases are the following. If the node is equal to null, then we are at the empty node and we should just return. Then we have a very interesting base scenario. I have actually created a set of nodes that we have already visited, and basically if we have already visited the node, there is no need to visit it again. Why this can happen in theory? Let's take a look. Now that we have added this third transition, it's possible that we will come back to the node that we have already visited. For example, if we are at the node 5, one of its recursive call will be, for example, to its right child, so to the node with the value 2. But one of the recursive calls from the node with the value 2 will be to its parent, so we will go back to 5. But we don't need to view our node 5, because first of all, we have already visited it, and second of all, the distance will be incorrect, the value of this parameter distance. So we need to prohibit such transitions, and we basically just check. If we have already been in a vertex, then we stop. Okay, so our third condition in a base is that if distance is equal to 0, we are simply adding this the value of this node to the result and once again return. Okay, now let's move to our transitions. So first of all, we add our current node to the set of visited nodes, and then we just simply recursively go to our left child, right child, and our parent node. And that's pretty much it. Okay, let's talk about the complexity of this solution. So in our collect parent data, we visit every node exactly once. And our find nodes at distance function, we visit every node no more than 2 times. And this means that our complexity is big O of n, where n is the number of the nodes in the tree. Okay, another point that I'd like to make is that we can avoid recursion, because these two functions that we have, collect parent data and find nodes at distance, they simply traverse the graph. And here we are traversing it with depth first search, or DFS. But nothing stops us from writing breadth first search, or BFS. This way we will avoid recursion, and probably this will save us some resources. Okay, and the final point that I'd like to make is what lessons can we take from this problem. So the first lesson is suggest multiple solutions to your interviewer. So for example, in here, you can tell to your interviewer that I can implement this solution recursively or iteratively, or you can even mention that you know the concept of lowest common ancestor, which is applicable to this problem, but I think it's a bit of an overkill. And okay, and the second lesson that I'd like to mention is suppose you have a couple of solutions in mind that are equally good complexity-wise and yeah. Otherwise, but one solution you know that you'll be able to implement it really good, really fast, and your interviewer will be impressed. Then obviously choose this solution that you are confident in, and this will increase your chances of passing an interview significantly. Okay, guys, thank you very much for your attention. I hope you liked this video. I certainly liked recording it. So if you did like it, please press like, subscribe, and I will see you around. Thank you very much. Bye bye.